If a spin is completely isolated, our usual notion is that it retains its spin vector property. But not for a subquantum particle. They are quite different. First, the two axes of quantization are indistinguishable, which is not true in the presence of an anisotropic probe. And so the two indistinguishable axes of quantization superpose to give a Hermitian state of √2 greater in magnitude than at the usual spin 1/2. It lies along a vector that bisects the two-dimensional spin. This √2 spin is a new state of matter that cannot be predicted from quantum mechanics or the Dirac equation. It is a unique subquantum resonance of a single spin between two internal magnetic moments. Many examples of resonance are observed in microscopic particles, and this is just another. Recall earlier I mentioned that resonance and indistinguishability are two properties of the microscopic that do not occur in the macroscopic. See my blog entry 5. The fact is, this is a pure dispersion-free state of one spin. But symmetry breaking involves degeneracy, and here this leads to subquantum exchange spins in each of the four quadrants. So the subquantum theory predicts that an exchange spin exists in four basically equivalent orientations. Because the four orientations a spin can take are degenerate, all we can say is that at any instant of time it is in one of those orientations. It resonates between them. This picture of an isolated spin is quite different from predicted from quantum mechanics. It is as if, in the absence of any interaction, a spin sort of shuts down into a resonant state of zero angular momentum. For an isolated spin, recall that quantum mechanics predicts a spin to have a vector magnetic moment and two states of +1 and -1. A subquantum spin, in the absence of all interactions, is a resonant state of net angular momentum of zero. As I will show, exactly the same sort of situation occurs for two subquantum particles in a singlet state or the other Bell states. The second major consequence of the subquantum theory is that the Bell states are separable. The sum over all these terms leads to cancellation of many terms, leading to the usual isotropic singlet state. The 8 terms organize into 4 Hermitian pairs. Each pair, being a singlet, has opposite angular momentum, and the phase gives 2 orientations. First row, plus plus, minus minus. Second row, plus minus, minus plus. Third row, minus plus, plus minus. And fourth row, minus minus, plus plus. Each spin pair has opposite angular momentum. Each row is Hermitian and a product state. It's not entangled. That is, the singlet state of one pair of spins. So you see what I mean when I say the singlet is like an isolated spin, because it has 4 Hermitian terms which resonate between the quadrants in a state of zero angular momentum. It is not hard to imagine that combinations of more spins will lead to a similar sort of Clebsch-Gordan coupling. I write each of the 4 product states as single terms called biparticles. That is, each row in the last slide is written as one of the 4 possible Hermitian states, and these are the biparticles. Now, it is fundamentally important to the theory that when 2 particles in a bound singlet state separate, they can only decompose into one of the 4 biparticles. It is also assumed that one spin moves towards Alice and the other towards Bob. Then they are only correlated by having microframes which have identical orientations relative to the laboratory axis. This is why they are called biparticles. They share the same hidden variables. Just to see this explicitly, now simply multiply out and collect terms. And we find that each biparticle can be written in terms of Pauli spin vectors and reveal, as might be expected for the product of 2 vectors, the usual isotropic scalar part. This is the quantum mechanical result, by the way. In addition, there are 2 vectors pointing oppositely, as they must for a singlet state, and a symmetric traceless second-rank tensor. These are the extra terms predicted by the subquantum theory. If we sum over the quadrants, that is, over nz and nx, then these terms all cancel, leaving only the quantum part. This is the subquantum state for two spins. From this, all the correlations of EPR experiments can be calculated. In particular, the coincidences agree with the data and are products with no entanglement. The quantum result is just a constant of 1/4, but that is not the case here. Each spin is filtered along a different direction and defines a subensemble with specific orientations. So, summary so far. Subquantum spins have two-dimensional structure oriented in a microframe. Indistinguishable axes of quantization predict a new exchange state. Degeneracy between orientations in the microframe leads to a resonant state of net zero angular momentum. The Bell states separate into products of two-dimensional spins that also display resonance between the four Hermitian states called biparticles. Upon separation, the biparticle product state remains correlated because both spins have the same orientation. In the next part, I will talk about the subquantum ensembles.